Hi everyone. I think it looks like about the right number of people are here. Can I just check if someone could unmute and let me know that you can hear me? That would be good.
Yeah, we can hear you.
Thank you very much. Okay, if you're ready, I will cut straight to the chase and continue where we left off last time. So that's just a test of, I'm assuming this is the right way up for you. So these are Daniel Fritsch's notes, but I'll carry on making my own notes. We are recording already. And I'll just remind everybody where we were last time. We defined a group. We defined class structures within a group, which we saw was in some way lumping together similar types of symmetry operation if we're talking about symmetry groups. We talked about matrix representations. I'll write it out in full once. We defined character, which was essentially the trace or the sum of the diagonal elements of a matrix representation. And we showed that all the symmetry elements within the same class have the same value of the character. So that's independent of the basis that you chose to write those matrices down. The character is the thing that's preserved. And that can be proved. We're skipping a lot of the proofs because that gets quite mathematical. And what I want to do really is give you the confidence by trying to make a difficult subject look simple. Or to get you familiar enough with the language that you could teach yourself more if you ever need to. So with the matrix representations, the idea here is that we're heading towards an abstract theory of what the symmetry of the system does, independent of what basis you've chosen. So you're trying to discover the structure of the eigenstates of a quantum problem, typically in physics. And it's very likely that the natural basis that you use to describe a system isn't actually the basis that best describes the eigenfunctions. So if you think of vibrations of a molecule for a second, then an atom, we might attach x, y, z coordinates to an atom. But in fact, when you put it in a molecule, let's draw a molecule, then we might have a vibration like that, where the vibrational modes has these atoms moving out of phase with the central one, whereas I might have attached the z coordinates pointing in the same direction for all three. So it's the process of how we get from our naive kind of way of constructing a representation to the real symmetry properties of the eigenstates that this is about. So the first question we're going to ask, continuing the theme of matrix representations, is, are there special representations? And we're on about page 10 of Daniel's notes if you want to correlate what we're doing with what he did. So if we have a group G, which is a set of elements, as we've written a few times now, and some rule for combining them, then we can consider what happens when we apply a similarity transform S to these matrices. So E will map onto E prime where E prime is S to the minus 1 E S. So remember, E is a matrix, S is a matrix, so that if you had a vector in the space where you set up E, then S times that vector would map it into the new space. And to map a matrix into the new space, you multiply by S to the minus 1 E S. That's basically the algebra. A prime would be the same, S to the minus 1, etc. Then we can say that the transformed set G is also a group and a representation of G. And we can prove that. I said I wouldn't do too many proofs, but this is a nice one because it gives the flavor of how a lot of them work. So let's suppose that A and B combine in G to give us an element C, then, not writing the star anymore, A prime acting on B prime, we can expand, is S to the minus 1A S, S to the minus 1B S. You can see that we're going to use associativity again. So that's going to be S to the minus 1A S, S to the minus 1B S is S to the minus 1AB S equals S to the minus 1C S equals C prime. So reminder what we're trying to do. We're showing that a similarity transform doesn't lose any of the structure of the group, so that if we have an A, a B, and a C that combine so that AB equals C, then A prime, B prime equals C prime. And the interesting question here is, that if A prime and B prime are now block diagonal, then we can number the blocks for clarity. So let's suppose that A prime is a matrix which has a matrix 1, matrix 2, matrix 3 in blocks along the diagonal. Then if we consider the matrix 1, if we're acting on some other matrix which is also representing G prime, then this matrix 1 will only act on that block of this matrix. And so we can say that A1 B prime 1 will equal C prime 1. So that if this was B prime, and this is C prime, what I'm saying is that this block matrix here multiplies that block matrix and gives me that block matrix in the structure, and so on. So, and same for the second block, that will equal the second block in C, etc. Which implies that the blocks 1 are also a representation of G, because they all multiply in the same way. Blocks 2 are also a representation of G, and so are blocks 3, etc. And a very obvious statement these blocks along the diagonal are smaller than the matrix they belong to. And that leads us to ask, can we shrink these blocks smaller and smaller? And the answer is effectively no. There comes a point where the matrices don't get any smaller, or if you like, the technical term is where we reach the stage where the matrices are irreducible, so that if the representation A prime, B prime, etc. here were irreducible, then let's say block 1 is a 2 by 2 block. What we're saying is that there's no more similarity transform left that will reduce this to a 1 by 1 completely diagonal form. So our mission, when we've constructed our arbitrary representation with our arbitrary starting basis, is to find out how far we can reduce these matrices to a block diagonal structure by similarity transforms. And in reality, by the end of today, you'll see that we don't really have to do that by blindly searching for similarity transforms. We're going to use this property that the character is invariant. And the character will help us find out what the block diagonal structure would look like if we were able to find the similarity transform. Okay, so first of all, I think it's interesting to prove that character is invariant under the action of a similarity transform. This is textbook stuff, and if you ever really needed to know this, then of course you will want to go back to a textbook. But I think it's, again, it's nice to see how these proofs work. So consider some general group element R, which is similarity transformed to given R prime. Then the character of R prime is defined as the sum of the diagonal elements of R prime. And now let's write out this sum completely explicitly. So that's when we substitute for this transformed R, then we've got a matrix multiplication. So we're going to have an S to the minus 1 ij multiplying an rjk multiplying an ski, and we're summing over I and j and k. So that's got the matrix multiplication, that's rjk times sk something, and then s something j times rjk. That's standard matrix multiplication. And then I've made I here and here equal. The final sum over I is what gets me the trace of the matrix. So that makes this a single number. It's going to come out of this. We've summed over all indices. So this is just going to be one number. And we can reorganize this because each of these is also a single number. Now, ski times s to the minus 1 ij, that's going to be the identity element, we've still got three subscripts k and j. So this is going to be the unit matrix kj, having carried out the multiplication summing over I. So this is ijk here, but we've done the sum over I here. And that equals, if we sum over k here, that equals rj, because the identity element, the identity matrix, if you like, is turning all k's here into j's. So the sum over j of rjj is, by definition, the character of R. So this is important enough that it's worth a separate line. So under this similarity transform, the character of the representation is the thing that is invariant. This means that this is why it's not going to matter what particular basis you use, because when you calculate a character from it, you're going to get the right answer. And when you block diagonalize via a similarity transform, the character is going to be the thing that's unchanged. So I've introduced the word irreducible once already, but let's say it a little bit more formally. If we can find S such that A prime equals S to the minus 1A, S is block diagonal, then representation A is reducible. So in general, this is how it will be. You will set up a representation. It won't have a block diagonal structure in general. But if you can find a similarity transform that block diagonalizes it, then it's reducible. If it is already block diagonalized completely, then you've, by luck, hit on an irreducible representation right from the beginning. Okay. Pause just to check that everything is working for everybody. You can read what I'm writing. You can hear me still.
Working over here.
All okay?
Could I ask a quick question?
Yes.
Just on this last part here, when you say if you can find S such that, you know, A prime is block diagonal,
Yes.
does this have to be true for every matrix in the representation?
Yes. Yes. So some will be more block diagonals than others. If you think of the identity element in any representation, that's going to be ones down the diagonal, noughts elsewhere.
Yeah.
So it's no work, it's a pushover. But if your A matrix has a 2 by 2 block here, then we should think of that as a 2 by 2 unit matrix on the block there.
Right.
So yeah, they will all have the same structure. And I should reassure you by saying we don't have to find S. So we're not going to have to find the similarity transform. We're going to sidestep that. But my statement here is to say that if we could find an S, then the matrix representation is reducible. We're going to find that we can test whether it's reducible without actually having to find the similarity transform that we need.
Okay.
Thank you. So we now come to the grand or great orthogonality theorem. And if you ever want to learn more about this in detail, then the way I'm writing things down from now on will give you a clue. If you look at a web page and it's incomprehensible, then you're looking at one that's aimed at pure mathematicians. If you're looking at one that never even mentions the great orthogonality theorem, then roughly speaking, you're looking at a web page that's aimed at experimental chemists. And the level I'm pitching this at is really at the level of computational chemists, solid state physicists, so we're not going to try and do particle physics with this, but we are going to be interested in the theorem that everything is derived from. So this says, and I am trying to stick to Daniel's notation. Let me just check in the notes that I've given you. We've made it to page 11 now. And I'm going to write out what he's written because I'm going to dissect it a little bit. So we have a sum over elements of group R of matrices gamma from the ith representation representing group elements R, and they're matrices, so they have two subscripts m and n. So gamma I of R mn is a number. It's just a pure number, and there are m times n of them. And then we have another matrix, gamma from the jth representation, representing the same group element as this one, with also two subscripts, so they must be different, so m n prime. And the theorem states that that is equal to h, the order of the group, over root size of the ith representation, size of the jth representation, delta ij, delta m m prime, delta n n prime, which you've got typed in Daniel's PDF, so we don't need to worry about that. But let's just say h is the order of the group. So that's the number of group operations R's, the number of R's that we have. The dimension of the irreducible representation I is Li, and irreducible representation J has dimension Lj. R are the group elements. So there are a lot of ways of thinking of this. It's a bit like a dot product. So if we concentrate on keeping m the same as m prime and n the same as n prime, like these two deltas say we should, then we're summing over the R elements of the group, and we're taking this value times that value over this vector of group elements. So this is like a dot product in an h-dimensional space, and it's like a whole bunch of them. So for each m prime and n prime set of values, there's a dot product of this h-dimensional vector. I attempted to draw a picture of this. Whether it's helpful, I think probably I'm going to skip my picture of it because I think it's probably actually slightly more confusing than it need be. Now Daniel lists some simplifications of this. So let's just write them out because I think it's helpful to talk through them. The first is that vectors from different reps are orthogonal. So that's saying that the sum over group elements of gamma I are gamma j are, even if I make mn and mn here the same, that equals naught if I is not equal to j. So these guys have to come from the same representation. If they do, then we have a simple result. So if I make this gamma I, so this is his third bullet point, in fact. So we have vectors, sort of vectors, or h-dimensional vectors over the group elements. If they're from different representations, they're 0, and if they're from the same representation, then they've got a very well-defined magnitude. So they are a kind of orthonormal vector of a very abstract kind. And where we go with that is to construct character tables. And now we're getting to things which occasionally you see put in papers, or you certainly find in textbooks. So this is page 12 of Daniel's notes, and maybe it's easiest, you can't read this exactly, but I can point to the comments that he makes. From the great orthogonality theorem, we can move from sums over all of the matrix elements to sums over the characters. So we can restrict those m and n. I'll show you how this is done, to derive orthogonality conditions also for the character vectors. And this is very powerful. So there are a set of rules here. All of these are provable from the great orthogonality theorem. And that's too much textbook space given that we only have 4 hours total. But the number of irreducible representations in a character table is equal to the number of classes in the group. The characters of all symmetry operations in the same class are equal in each given irreducible representation. Now we've effectively proved that because we've shown that the matrices transform, the C transform to C prime. And so we're very close to proving that. The sum of squares of all characters in an irrep is equal to the order of the group, etc. So let's do something which Daniel didn't quite do, and let's look at one of these proofs. So we take our sum over group elements, gamma I, R, M, N. We're not going to have to write this out very much more. R, M prime, N prime is H root Li, Lj, delta Ij, delta M, M prime, delta N, N prime. And let's suppose that we put M equals N, M prime equals N prime, and sum over M, M prime. That's going to give us the product of the traces of these matrices. The group elements sum is still there. And the delta Ij is still there, but we've used the other two deltas. So this is a new orthogonality theorem We can simplify this even further, and I think this is not in Daniel's notes. We don't need to sum over all group elements. If the character is the same for every R in the same class, then we just need to know how many R are in the same class, and then we can make a weighted sum. So this will simplify to a sum over classes P now of the number of elements in a class times the character in the ith representation of that class times the character in the jth representation of that class, and that's going to be the same right hand side, delta ij. So this is the same orthogonality theorem as above, really, but this is for classes now. And this is going to be very handy because we could ask, is a representation reducible? Well, I've asked that once today, and I've said, yes, it is if I can find a similarity transform that block diagonalizes its matrices, but that's a pretty tricky thing to deal with. I want something a little bit more straightforward than that, and we have it now. So let's suppose, going back to the orthogonality theorem for characters, if we took the sum over group elements for the character of the ith irreducible representation, and then we take our test characters for the jth representation, then what can we say about this sum? Well, if the jth representation is reducible, then that means that it's got blocks along the diagonal. It's got more than one block along the diagonal. And therefore, this is always going to be larger. Think of the identity elements. It's the trace of that is the same as the dimension of the matrices. So if this thing can be diagonalized into several blocks along the diagonal, its trace is going to be larger than the trace of any single one of those blocks. So if this is larger than H, then the representation that we've plugged in here is a reducible one. Okay, what's the time? About 20 minutes more, that's fine. At this point, we are definitely in need of a kind of practical exercise to make this all look a bit easier. So I'm going to use the one that Daniel has created on page 12 of his notes, example 1, which takes the water molecule. The connection to everything that we've said becomes clear by the end of today, I think. So here's a water molecule, an oxygen atom, 2 hydrogens. It's not straight. That makes its symmetry slightly more interesting. Its symmetry operations are the identity. There's a rotation axis by 2 pi divided by 2, so a C2 rotation axis. And then there's, let's draw it again, there's also reflection symmetry, which is usually symbolized by a mirror plane and the symbol sigma. And there's also, if it's a 3-dimensional space that we're looking at it in, then there's a mirror plane that reflects. And since the molecule has a finite size, this isn't a trivial thing. This needs a different symbol, so it's given a sigma prime. As an exercise, if you want one, the class structure is identity in a class of its own. Well, we knew that. The rotation in a class of its own, rotations are different to reflections, so that's fair enough. You might have guessed that the two reflections, being the same sort of thing, would come out in the same classes, but in fact they don't. And that's because the mirror planes are orthogonal, and in this case, they actually come out in separate classes. In some other example with a different point group symmetry, these reflections might come out as related to each other in the same class. But in this case, they're not actually mapped into each other by any of the other group elements. So we have 4 classes. So by the statements which we have in section 3.1 here, we have 4 irreducible representations. So that's 4 different sets of matrices that can't be block diagonalized any further than they already are, that are different to one another and obey the orthogonality relationships that we've just written down. So from rule 5, the sum of squares of dimensions of the irreps comes to equal the order of the group, then that means that if we have 4 irreducible representations and each of them has a dimension Li, and we sum Li squared from irreducible rep 1 through to 4, that equals H, the order of the group. By inspection then, H also equals 4. Let's pop that up here, because we have 4 symmetry operations. So H equals 4. And if I'm trying to sum 4 squared integers to get a sum of 4, then clearly the dimensions of the 4 possible irreducible representations all have to be 1. We can discount the negative sign because this is a dimension of a matrix, so it's got to be a counting number. So we have 4 1-by-1 matrix representations that are irreducible. At this point, we can draw a table. Do I want to use rule 3 yet. I'll just tell you, I see it's mentioned in Daniel's notes that the name of this group is C2V, and that's derived from the symmetry operations that it contains in a rather simple way. And we can write down the classes or representative elements of each class. So we only have to write one of each class, and we can write down the characters that these have for the 4 matrix representations that we have. So taking the first matrix representation, and remember what I'm looking for are 4 1-by-1 matrices that multiply in a way that is homomorphic to the combinations of these symmetry operations. And the most trivial example we'll start with is where I represent each of these symmetry operations by a matrix which just contains 1, because multiplying 1s together will reproduce in a non-faithful, non-isomorphic way the multiplication of all of these elements. Those are the matrices, but of course, because they're 1-by-1 matrices, their character is also either a plus or a minus 1. So our first set contains just 1s. We've got, how about 3 there? 4 irreducible representations, and they have to obey an orthogonality for characters, so that if these are the characters of E, C2, sigma V prime, in the first representation where I choose entirely plus 1s, then to construct an orthogonal character vector for the next irreducible representation, I have to have some minus 1s. So if I put 2 minus 1s there, I've got only 2 more ways I can distribute minus 1s, since the character of the identity is always going to be plus 1 all the way down, because it's definitely the unit matrix, so that contains a 1, not a minus 1. So the character of E is going to be 1 in each of these representations. So that column has to be 1s. This row I've chosen to be 1s as a starting point. And then in each of these, to obey the orthogonality relationship, I need to have minus 1s. So if I think of a dot product now of the top vector with the second vector, then that equals 0, as it should do, because if I go back to the orthogonality theorem for characters, whoops, you can't see that. This vector dotted with this vector has to be 0, because they come from different irreducible representations. This is I equals 1 and this is j equals 2. So the delta ij has killed that off. Does it matter that I've chosen gamma 2 to have the minuses here, gamma 3 to have the minuses here, and gamma 4 to have the minuses there? Not in this particular example, but there are naming conventions when we get to slightly less trivial groups. Will you ever need to know how to construct a character table? Probably not. If you're dealing with crystal symmetries, so space and point groups, then all of the character tables are already constructed. But I think it's important to understand how they work in a bit of detail. That's what this course is aiming at. So I'm actually making slightly faster progress than I planned, but we have about 10 minutes before it's a logical place to take a break. What I'm planning to do is to skip Daniel's example 2 on the ammonia molecule and the symmetry group C3V and jump to page 15 on using character tables. I recommend, if this is stuff you really want to understand, then you are going to need to go through his notes a little bit more carefully and probably to use a textbook. What I'm trying to do here is give you an idea of the level at which you need to be looking at things so that you don't get put off by some of the very, very tough group theory that you can see online if you Google stuff. I'm not sure about Wikipedia, but it's very easy to get out of your depth if you are looking at pages that are aimed at pure mathematicians. And a lot of the formality is unnecessary when you're dealing with the really simple groups that we're interested in a lot of the time. So I've used the triangle group as an example quite a bit, and that's why I wanted to skip to page 15, because that's the example that Daniel has given here. So we had, for the triangle group, 3 classes. The identity is in a class of its own. We can prove that. Then we've got 2 threefold rotations about the axis passing through the center, and 3 mirror planes, which now are related to one another because they're rotations of each other under this operation. So they all come out in the same class. And the number of elements in each class is 1 here, 2 here, and 3 there. So we've got 3 classes. And now we have a slightly less trivial situation because we've got classes that have more than 1 element. And the way I would conventionally write the character table for this guy then is E2C3 to remind me of this factor C, and 3 sigma V. And if I have 3 classes, then I must have 3 irreducible representations, which everybody calls irreps. So I can give these names. I'll just call them gamma 1, gamma 2, gamma 3 for now. So the order of the group, H is 6. And we can go back to the orthogonality theorem for summing over classes. So I shall just write that out again. Because we've now got a CP here. Obviously there's a 1 there, 2 there, 3 there. So if we are trying to take a dot product of the character for gamma 1 with the character for gamma 2, for example, then we've got to remember to put this weighting factor in. So the sum of squares of dimensions of the irreps equals H. That was rule 5, page 12. Provable from the great orthogonality theorem, and if you want to see how, that's probably a textbook job. So this means that for gamma 1, we've got, well, for these three gammas, we've got to find 3 different ways of summing squares up to get 6. So clearly we can sum 1 squared plus 2 times 1 squared plus 3 times 1 squared equals 6. So that's consistent with having a character of 1s all the way. And this is obviously a 1-by-1 irreducible representation because the trace of the identity element is 1. So these are 1-by-1 matrices, and all of them are 1. And if you think about it, 1-by-1 matrices all containing a 1 will always represent any group. So the first row of a character table like this is always going to be 1s because it's always going to be a very non-faithful homomorphic representation. There are more interesting representations to come, but this is always one of the set. So this has to be true. And if your sum across this row doesn't equal h, then it's because you've forgotten to multiply by the c's. For gamma 2, you'll have spotted that I can put some -1s in, and that will, because we are squaring the LIs, that will also be capable of summing to 6. And it might look like there are a lot of different ways that I could put -1 in here. But remember, we want gamma 1 dot gamma 2 to equal 0 from the orthogonality theorem for characters, which I've written out here. So if we're taking a dot product here, we've got to have +1 times something plus 2 times 1 times the next thing plus 3 times 1 times something equals 0 for the new elements that I want to add. And that's only going to work if I make this guy 1, this guy 1, and this guy -1. So we've got a 1, a 1, and a -1. And if you pop back to page 15, you'll see that that's true. And then for gamma 3, we have run out of the ways of adding plus and -1 squared to get 6, but we can have a 2 plus a 4 and a 0. So if we put a 2 and a 1 here and a 0, then 2 squared plus 2 times 1 squared is 6. Sorry, that's 1 times 2 squared plus 2 times 1 squared plus 0. That will equal 6. But if I make this a +1 here, then it won't be orthogonal to gamma 1. So to make it orthogonal to gamma 1, this row, this column is not a problem because that's 0, but we need a -1 here. So that gamma 3 dot gamma 1 is now 2 times 1 minus 2 times 1 plus 3 times 0 is 0. So that's right, that's right. So we've gone through the same exercise of constructing this character table. Let's stop there and carry on a little bit at 3 o'clock. Finishing a couple of minutes early, so if there are questions, fire away.
I actually wondered if it might be possible during the break to see your very first page of your notes, because I was a couple of minutes late. Didn't quite catch. I started jotting it down when I got here, but you'd sort of moved on before I finished.
That's fine. And that reminds me to say that the recording of last week's sessions has been made available to you now, I think.
Great.
And this is being recorded, and this will be made available the same way. So that's all going to happen.
Ah, great. Thanks.
So the first page of my notes is a little bit out of order, but I think that should be the very first page. Does that make sense?
Yes, thank you.
There you go. Okay, see you all at 3. And I will stop recording just for the moment. Hi. Not sure that we have absolutely everybody back yet. I'm happy to hang on just a minute longer.
Would it be okay to ask a question while we're waiting?
Yeah, sure.
It was about the irreducible representations.
Yep.
So I'm just trying to understand that. I'm looking back at the printed notes, which says it's the irreducible representations of a group that are of fundamental importance.
Yep.
And so I was just thinking, is it really the irreducible representations we want that are of the appropriate dimension? Because presumably, if you use like the trivial representation, for example, of the identity, that's irreducible, presumably, but it's not much use, I would guess.
That depends. So if you think of one of the easiest examples to visualize is a vibrating molecule.
Right.
Okay. And one of the vibrations that all molecules will have is a thing called the breathing mode, which is where the molecule just expands and contracts. But every bond length is expanding the same amount,
Right.
Proportionately, not absolutely. So there's no distortion of the shape of the thing. The symmetry is preserved completely. And if you think about how that vibrational mode would transform under all the symmetry operations, it's invariant under all of them.
Right.
Okay? It's not a mode where one part is going in a different direction to the other. That totally symmetric mode, if you construct that in a way that I might have time to talk about today, that transforms as the trivial gamma 1 irreducible representation of the point group symmetry for the molecule.
Okay.
Because that's a mode which, if you like, can be described by just one coordinate. It's just expand the molecule, contract it.
Okay.
So that trivial looking irreducible representation is actually the representation that labels eigenstates that completely preserve the symmetry of the system.
Okay.
And so if you were talking about Raman modes of a transition metal chalcogenide, for example, people talk about A1 modes. A1 is the conventional name for this gamma 1, I've called it.
Oh.
And so it's a very important
Okay.
irreducible representation, in fact, and it's ubiquitous. And it is. The fact that it's trivial doesn't mean that it's not important.
Okay.
Whereas the two-dimensional representation, so I have to find where my notes went. I think this is actually in the printed notes. I think Daniel has labeled this as A1. Where have my printed notes gone? It's chaos in here at the moment. Yeah. This is the conventional name. This one is conventionally called A2, and this is conventionally called E. And the reason for the A's basically is wrong camera. Sorry, I was just writing on a piece of paper there. The thing I've called gamma 1 is conventionally called A1.
Oh.
because A is a good place to start and 1 is a good place to start. This is another A-type mode because they are clearly very similar, but people use a completely different label for this type of mode because it's twofold degenerate. So for twofold degenerate modes, people tend to use the symbol E. So this is the totally symmetric eigenstate of the system. This is a twofold degenerate eigenstate of the system. And you can tell that because its identity matrix is a 2x2 matrix, which needs a two-dimensional basis.
Right.
So that means there are two eigenstates that correspond to that state. And so you can guess, if we're talking about vibrations of a molecule, that these are vibrations that are orientated in the XY plane, in the plane of the triangle, because there's no difference. I need two basis vectors to map out the XY plane.
Yeah.
The third one is redundant. But there's no fundamental difference between these two vectors. I could have drawn them anywhere in the 2D plane and they still do their job. So that means that any eigenstates that transform like them are going to be doubly degenerate. So these guys, if we're talking about vibrational modes, are symmetry preserving breathing modes. These are displacements in the plane where you can displace in two orthogonal directions in the plane with the same frequency.
Okay.
This course deserves more than 4 hours.
Yeah, I'm sure.
So I hope I'm not making it more mysterious. I'm trying to make it approachable because there's such a lot of formalism. And I hope I'll get to the point where I can show you how we do some things with everything that we've built up. So I've just been looking through some old lecture notes to see what things I could collect together. Anyway, I'd like to go beyond what Daniel did, but that's a little bit unwise because I think he had more time than we did.
Oh, yeah, that's a shame. But I mean, you did point out that we sort of, you're preparing us to sort of fill in gaps and look in the literature to sort of find anything we need. So I appreciate that.
So everyone, if you're happy for us to kick off again, I think we're ready to go. I may have gone a bit faster than I intended in the last hour, so I may be able to slow down a bit this hour. We'll see how it goes. I won't count my chickens, but I have one or two things I might add in if we have a little bit of extra time left. And anything I say from now on is going to be about the usefulness of this, because I've said very little about that so far. That's just how it is. So we finished by effectively constructing the character table for the triangle group. So we've just written that down, and I've just been saying that there are conventional labels here, and that's in the printed notes. We've used the orthogonality theorem for characters weighted by the number in a class, so using a sum over class. So that's basically, we've just confirmed that dot products of these vectors weighted by the factors that are across the top here is satisfied. And you can look at tables of character tables. They're in many textbooks, just to confirm that all of this happens. So a bit more light. So we've confirmed that, for instance, that gamma 3 is orthogonal to gamma 1, gamma 2 is orthogonal to gamma 1. And this, first of all, is how the character table is constructed, but it's also how they're used. So if we consider now a reducible representation, well, I've got to make up one. We'll stick with the triangle group. We did make a 3 by 3 representation previously. So the identity element was the 3 by 3 matrix. C3 was cos 2 pi by 3, sine 2 pi by 3, 0, 0, 1, 0, 0, 1, and then it was a minus sine cos. And the sigmas had, let's do one of the sigmas. So if we're going to reflect in, we're going to reflect that, and let's say that I put my x-axis along there, then it's going to reflect to minus itself. The y-axis, if I put that there, is going to map onto itself, and the z-axis is going to map onto itself. So that's one of the sigmas. And if we look at the traces of these, then the character of the identity is trivial because that's the dimension of the matrices, so that's 3 by 3. The character of this C3 matrix is, well, that's minus a half plus minus a half plus 1 is 0. You might say, aha, but what about the other C3 rotation? That's a different matrix. Yes, but they're in the same class, so we've proved they have the same character, so I only need one example of each of these. And the same for the sigma, the trace of this one, which was mapping x onto minus x, so the mirror plane is the one that's here, mapping y onto y and z onto z. The character of that is minus 1 plus 1 plus 1 is 1. So our character vector for our 3 by 3 representation is 3, 0, 1. Stop me if anything goes too fast. And again, you might have said, aha, you chose the reflection of x into minus x because it was easy to write down the matrix, but it would have been more difficult to write down one of the other reflection matrices. Well, maybe, but because they all have the same character, because they're in the same class, it was sufficient to use this one. So we've got a character vector for our 3 by 3 representation, and we immediately see that that's reducible. How do we know it's reducible? Well, because it's not in this table. So the simplest statement, once we admit that we can just look up character tables in a book, is that the character I've just worked out isn't one of these, and therefore it must be reducible. But we've also got a test. So I mentioned this test here. This was on an earlier page today. Is the representation reproducible? Well, if I take its character vector dotted with the character vectors of the irreducible representations, then I will find out how many times the ith irreducible representation is contained inside the reducible representation. So I want to see an example of that. So we'll just carry on for the moment. The character of the 3 by 3 representation is reducible. Firstly, because it's not in the character table. Okay, so it's not one of the irreps. And secondly, we use the orthogonality theorem, which is a bit more defensible and formal. So if we take chi 3 by 3 dotted with the irreducible representation gamma 1, sorry, only gamma 1 character vector, that would be three, 0, 1 dotted with 1, 1, 1, but we must remember the multiplicities of these. This is times 1, this is times 2, times 3, because that's the number of elements in each of those classes. So that equals 3 times 1 is 3, plus 0 times 1 times 2, plus 1 times 1 times 3 equals, if we sum 3 plus 0 plus 3 equals 6. Now, so in this case, this is, because this is such a simple example, this implies it's not actually larger than h, but if we take chi 3 by 3 dotted by chi gamma 1 divided by the order of the group, which is 6, what this tells us is that the 3 by 3 reducible representation contains gamma 1 once. So we'll actually go back to the matrix structure in a minute and see that that's true. But if we take chi 3 by 3 dotted with the character for irreducible representation gamma 2, then we have 3 0 1 dotted with 1 1 minus 1 times 2 times 3, and pretty clearly that will equal 0, because we'll have a 3 times 1 minus 1 times minus 1 times 3 will equal 0. And we see this still, yep, gamma 3 times by the character for gamma 3 is 3 0 1 dotted with the bottom row of this table 2 minus 1 0. Times by 1 2 3, that equals 3 times 2 times 1 plus 0 times minus 1 times 2 plus 1 times 0 times 3, and that also equals 6. So don't want to lose sight of this too soon. We'll keep that there just for a moment. So that implies that chi 3 by 3, the 3 by 3 representation contains gamma 3 once. So in other words, our representation contains gamma 1 once plus gamma 3. And because this isn't an algebraic plus, a lot of people would put that in a circle. And what we're saying is that our character vector of 3 0 1 has decomposed into the character of gamma 1, which was 1 1 1, plus the character of gamma 3, which was 2 minus 1 0. And this example is so simple that you could take a kind of cheeky shortcut to this answer, because if I just add these numbers, you can see that they add up to give me this character. That's not quite what we're really doing, of course. What we're actually doing, if we go back to our matrices that we wrote down, what we're saying is these 3 by 3 matrices are block diagonalizable because they're reducible. And if we attempt to block diagonalize them, normally we might have to find some similarity transform that did that for us, but we can do it by inspection here. The E matrix, well, it's always diagonal, so that isn't going to tell us very much, but I'll put it there for completeness. The C3 matrix is very illuminating because it's already what we've written down is actually block diagonalized, and the same goes for the sigma matrix that I wrote down. So we can see the underlying structure of everything here is that we have a 2 by 2 block and a 1 by 1 block. And in fact, that representation that we constructed was already block diagonalized. So this is sort of going back to a question that was just asked. The blocks are the same for all of the matrices. So although it's not obvious looking at the E matrix, it actually consists of a 2 by 2 block and a 1 by 1 block. And this sigma matrix consists of a 2 by 2 block and a 1 by 1 block. And what we've been saying today hopefully now becomes kind of clear, because what I'm saying is that there, from my 3 by 3 representation, there are 2 representations that make this up. One of them is the representation E equals 1, C3 equals 1, sigma equals 1 in 1 by 1 matrices. And that's clearly the gamma 1 representation, where everything is a 1 by 1 matrix containing a 1. And then the gamma 3 representation, E equals 1, 0, 0, 1. C3 is cos theta sine theta minus sine theta cos theta. Sigma is minus 1, 1, 0. And that's a 2 by 2 representation. The character of this is R1, 1, 1, which is the first row of my character table. And the character of this gamma 2 is 1 plus 1 is 2, minus half plus minus a half is minus 1, minus 1 plus 1 is 0. And that's the bottom row of my character table. So here are the matrices that I constructed in an arbitrary human readable basis of Cartesian XYZ coordinates to describe my symmetry transforms. I find out that it's a reducible representation. It reduces into gamma 1 plus gamma 3. And that's telling me that if I have some physics problem that depends on the basis X, Y, Z, that those are the states that I want to build the answer to my problem out of, then the eigenstates will be of form A1, being the conventional name for gamma 1, and E. In other words, I'll have a doubly degenerate eigenstate and a non-degenerate eigenstate, and this one will be an eigenstate that totally preserves the symmetry of the system. So if we jump to thinking of things like atomic orbitals, you can see that an s orbital is a highly symmetric thing, whereas a p orbital is less symmetric, and a p orbital is triply degenerate, whereas an s orbit is non-degenerate, setting aside spin. So you can see how these transformation properties relate to the fundamentals of quantum nature. Yes, far away.
Did the test that you'd previously given in the notes earlier, did that work or fail in this case? That's what I didn't quite understand.
Okay, I should go back. Yes, I shouldn't have put a greater than. What I should have done is divide this by h and say that that equals the number of times that j contains I. So maybe we better correct that. Yes, yeah, that was a slip of the brain at that point. If this is saying that this is non-zero, so if this product is non-zero, then my representation J contains irreducible representation I. Okay. That again, if this product is non-zero, then J contains I. And if I divide by H, I find the number of times that J contains I.
Right.
If J is reducible, then it contains one and one only I. And how?
Oh, right, yeah.
Yeah. How does that work? Well, what we've just done is the clue. If I had gone a bit crazy here and decided that I needed to write down much larger matrices, I could have written down rotation matrices. Let's say I had a couple of coordinates that I don't need. So I could have gone for a 5 by 5 basis. So E would have 5 elements. The C3 would have its 2 by 2 block. And then if these are really redundant extra coordinates, they're not going to do anything. And my reflection matrix would have contained its 2 by 2 block. And then had some extra coordinates which don't get affected. And you can see that what these extra coordinates are doing is adding to the trace of each of these matrices. And in this example, pretty clearly, I've included gamma 1 several times. And so when I take the dot product of my 5 by 5 representation with the character for gamma 1, or A1, that will now equal 3. So when I multiply out these numbers, I'll get 18, divide by the order of the group, which is 6, and that will give me 3.
Yep, that makes sense.
Yep. And if I'd included this 2 by 2 block twice, then I would find when I dot with gamma 3 with the E mode, I would find that I'd get 12 divided by 6 is 2. It would tell me that it contains the gamma 3 or E representation twice. So this dot product of your representation with the irrep here tells you how many times this irrep is contained in this. Makes sense now?
Yeah, so although in the instance you've just done of the 3 by 3, it contains 2 of the irreps only once, it's still reducible because it contains 2 of the irreps, not just one of them.
Yeah, exactly. So the trouble with a sort of simple example like this is that it does fall out really too easily for you to see it working. because it was already block diagonal. But you could imagine if I'd done something clever, I might have managed to camouflage the structure of it. So if I'd picked some really silly set of axes, then they would have mapped onto linear combinations of each other under these operations. So if I hadn't put the z-axis normal to the plane of the triangle, then these elements would be non-zero. But the trace vectors, the characters would still come out right. So the character of this 3x3 basis, this should come out right, independent of where I've put the axes, even if I put the z-axis somewhere silly, and even if I make the x-axis not orthogonal to y.
Yeah, thanks for that.
This is the thing that's invariant.
Yeah.
When I dot product it with each of the irrep characters, then I'll find out how many times that irrep is contained in this representation.
Okay.
It's really good that you ask that, because this is the kind of nitty-gritty now of doing calculations. If you imagine that you start with a system whose point group symmetry you know, so you can identify the name of that group and look up its character table, then these are the kind of sums you can do. You need to construct a basis for the physical problem you're trying to solve, work out the character of that basis, and that will tell you the structure of the eigenstates that you can construct from that basis. And if I have time today, I'll say just a little bit more than is in Daniel's notes about how you would actually construct the eigenstates now, because this looks so far like a sort of passive analysis of the system that you're dealing with, but you can actually use this as a tool to construct the solutions that you're looking for. So
yeah, great. Thanks for that.
In fact, yes, I think so I missed who it was who was asking questions, but taking you as kind of representative person, I think one more example of this whole thing in action would probably be very useful. We've got enough time to do it. And then the thing I want to tell you about that's not in the notes, more or less just to tell you a couple more keywords that exist, so that if you ever need to do these kind of sums, you know what else you need to be looking up in an index. Let's play with this triangle group a bit further though. So let's consider an actual triangular molecule now. And let's take about the simplest kind of problem, which is its vibrational modes. And so we're at the level of group theory for a standard chemistry course, really. They might not do any of the proofs, and we've skipped a lot of the proofs as well, but they would be interested in molecular vibrations. So we have an atom at each corner of this equilateral triangle. The atoms are identical, and I'm going to put coordinates on them to describe vibrations of the molecule. Okay, so I'm going to have a z-axis coming out of the page for this atom, but I need one for this guy, and I need one for this guy. So this is not just axes, these are three independent coordinates. In other words, I can move this guy up a bit without moving this guy up a bit. So z on each of these atoms is an independent coordinate, and I need a y and an x for this guy, and then I need a y and an x for this guy. I'm calling that y and that x, and then I need a y and an x for that guy. Can everybody follow my rubbishy sketch? Is that all clear?
Yeah, that's clear.
Good. So I've got three atoms, They are in a three-dimensional space, so I've got 3 times 3 equals 9 coordinates to describe the problem. And with those 9 numbers, I can describe any configuration of these 3 atoms in space. So this is going to give me a 9 by 9, well, not the, it's a 9-dimension basis. It's going to be a 9 by 9 system. So if you imagine the identity matrix for this system has to map 9 coordinates onto themselves. So it's got to be a 9 by 9 unit matrix. So the character of E in this basis is 9. Rotation by a threefold rotation. What is clear here, we're going to do this by common sense and inspection really, is that no coordinate maps onto itself. Okay, so this y maps onto this y under a threefold rotation, but that's a different coordinate in my starting basis. If you like, we could call this y1, z1, x1, 2, 3. And then it's a bit scruffier still, but it's clear y1 maps onto y2. So that's not a diagonal element in the representation matrix. So just by inspection, I can say that C3 equals 0, character of C3 in this 9 by 9 basis. And again, because the other C3 rotation is in the same class, I don't need to spend any time thinking, it will have the same character. And this same statement is true for the other threefold rotation, so that's okay. The mirror plane, that's a bit more interesting. If we take this mirror plane, for example, x1 goes to minus x1, y1 goes to y1, z1 goes to z1, because they both lie in the mirror plane. And all others, well, in this mirror plane, all the x3, y3, z3 map onto linear combinations of x2, y2, z2, so they don't map onto themselves, so they're not contributing diagonal elements in the transformation matrix that represents this operation in this 9D space. So everything else gives 0 to the character because it's off diagonal. So here we've got a -1. This guy maps onto minus itself. This guy maps onto itself. This guy maps onto itself. So our character for this reflection is 1. And so the character for our 9 by 9 representation matrices, clearly they're going to be reducible. That equals 9, 0, 1. Which looks awfully like what we wrote down for the simple 3 by 3 matrices, where we just allowed 1 x, 1 y, 1 z. So really there we were looking at the mapping of a set of Cartesian axes onto themselves under the operations of a triangle. Now we're looking at coordinates, spatial coordinates of 3 atoms under the symmetry operations of a triangle. We had a 0 here before and we had a 1 here before, but we've got a bigger number here because we've got more coordinates. And if we take chi in the 9 by 9 representation for dotted by A1, and remembering the weightings 1, 2, 3, then we've got 9 plus 0 plus 3 equals 12. So that means that we've got the A1 irrep appears twice in my block diagonalized 9 by 9 matrices. And you can see now why I said that I'm never going to attempt to find the similarity transform that block diagonalizes these 9 by 9 matrices. I haven't even bothered to write down these 9 by 9 matrices. I've written down their traces by inspection. It's not always so easy to do that. When you're talking about spatial coordinates, it is. So you might have to actually write down matrices and calculate things. Just pressing on with this example then, dotting with A2, we've got 9, 0, 1, dotted with 1, 1, minus 1, and that equals 6, because we've got 9, 0, and minus 3, so that equals 6. So we've got A2 now appears. We didn't have an A2 before, and 9 by 9, like our E mode is 9, 0, 1, 2, minus 1, 0, and that gives me 9 times 2 is 18, 0, 0, 18, divided by H, which is the order of the group, gives me 3E. So my 9 by 9 okay. And now we really are talking about vibrational modes of this molecule, because to describe a vibrational mode, this is exactly the basis I need. I need each of these atoms to be able to move in 3D space. And what this is saying is that the eigenstates of that Hamiltonian describing motion of these things in space will be 2 of symmetry type A1, 1 of symmetry type A2, and 3 of symmetry type E. So we are saying that there'll be 3 non-degenerate eigenstates and 3 pairs of doubly degenerate eigenstates, and all without writing down a Hamiltonian at all. If you were to do a Raman experiment on this molecule, this tells you immediately you're not going to see this guy, you're going to see this in a certain polarization experiment, and you're going to see this in a different polarization experiment. So this is immediately a key to interpretation, for instance, of a Raman spectrum, which is why the chemists are obviously interested in this, as well as much more challenging examples. Now, if we just consider a displacement along Z, so we consider the 3 displacements along Z, the character of a Z displacement is just A1. So we could write down a basis in which we just have Z coordinates, and that will give us an A1, and the character of X, Y displacements is going to work out as E.
Sorry, can I ask a question?
Yeah, sure.
If you look at the Z displacements, there are 3 of those, right? There's 3 Z coordinates. So how can that possibly be A1? Because that's 1D, right? There's still 2 more dimensions.
Yeah, I'm popping back to, where's my last page? I'm referring back here to what we did when we had just single X, single Y, single Z. They broke down as A1 plus E. Yeah, your question is absolutely right. But if you just remember for the moment, when we had a single X, a single Y, and a single Z, they gave us A1 and E. Okay, so if we have a single Z, that's A1, and a single X and Y are E, then if you imagine the molecule is rigid, so you set Z1 equals Z2 equals Z3, so that the molecule is not vibrating, it's just moving through space without vibrating, then linear motion without vibration gives me A1 plus E. So to whoever asked the question, sorry, I missed who it was. Do you see where I'm going with this now?
Yeah, if effectively you reduce the dimension by setting Z1, Z2, and Z3 to be equal.
Yeah, so I'm saying if we were to construct a Hamiltonian or an equation of motion, then one of the solutions is going to be no vibration. It's going to be simple translation of the molecule along the x-axis or along the y-axis or along the z-axis. And if I'm translating along the z-axis, then what I'm saying is that Z1 equals Z2 equals Z3. If I'm translating along the x-axis, then I'm saying that X1 equals X2 equals X3. So translating the molecule as a rigid thing is a solution of the equations of motion.
Oh yeah, okay.
And
I guess I was thinking of when you said consider the Z displacement of the 3 Z coordinates in total, and then as a subgroup of the 9-dimensional thing that we discussed above. And then you would also have, of course, vibrations included.
yeah,
That you would have like 1 minus 1 minus 1 or some
right.
kind of.
Yeah, no, so here I'm considering a rigid translation of the molecule without any vibration.
Okay. Yeah.
And but that will be a general, it will be a part of a general solution of the equations of motion for this. And so we can discount one of our A1 solutions and one of our E solutions, because one of our A1 solutions is going to correspond to linear translation of the molecule, and one of our E solutions is going to correspond to linear translation of the molecule. So this will correspond to motion normal to the plane of the molecule, and this will correspond to motion in the plane of the molecule, in which case there are 2 orthogonal possibilities for it to move along. So the vibrational states are basically this minus these 2. So an A1 plus an E2 plus 2, sorry, A2 plus 2E. Just pause for thought at that point, because we've done something really powerful now. And we've done it in the space of a page, which you can't quite see, but we've attached coordinates to the atoms of a molecule, and we've deduced that it has these 6 vibrational modes. So bearing in mind these are twofold degenerate, we've got 1, 2, 3, 4, 5, 6 vibrational modes, by which I mean that the frequency of vibration is not equal to 0. The linear motion, there are 3 states for which the frequency is 0, but there is still motion involved. So we've got
a quick question.
Yeah.
Sorry.
Questions are good.
The rotational states of the molecule.
Right. So they're going to be expressible as linear combinations of the linear motion. So if I want those to, how shall I put this? Yes, they're not new at this stage. So to make the rotational motion different to just being a linear combination of these linear motions. So here I've got motion along X and motion along Y. If I decided to rewrite those as X plus or minus IY, then I would have a description of rotational motions around the Z axis.
I see.
Yeah. And you will say, yeah, but those are different because the energy of linear motion is half mv squared and the energy of rotational motion is half I omega squared. And those are different. But now you're putting in physics that is beyond what the symmetry of the problem dictates.
I see.
So you can certainly write down a rotational displacement and work out what its character is. So I've chosen to analyze Z displacement to X and Y displacement here. I could have chosen to analyze a rotation around Z and rotation around X and Y.
Yeah.
And I would have got the same combination of irreducible representations, I think. I probably ought to check that's true. The point about the remaining vibrational states, sorry, it's gone a bit bright in here suddenly. Draw a curtain. The point about these vibrational states is that, well, here's our breathing mode, where the molecule is expanding and contracting, and we're always going to have that. That leaves the center of mass put, and the thing isn't rotating or anything. So that's any energy associated with this is entirely due to stretching bonds. And the same with these. This one breaks, is some mode where the symmetry of the molecule is broken. And the same with these. These are ones where the symmetry is broken. So these are all stretching springs. And the point is that these two solutions of the problem are not stretching any springs in the molecule. And I can have a rotational motion that doesn't stretch any springs or a translation motion that doesn't.
Great.
But what I do have to check, I started off with 9 coordinates. And if I add the solutions up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions. So I've started with 9 coordinates and I've got 9 coordinates at the end. So I haven't got any degrees of freedom unaccounted for.
Can I ask a follow-up question on that?
Yes.
You were saying that how A2 is stretches bonds and stuff like that. If you would have this decomposition and you would do Raman and you would measure the A2 mode, how would I now then go here and find out, okay, which coordinates are moving when the A2 mode is excited?
Yeah.
Because that's a 1D eigenstate that is part of this whole problem, but how do you find that eigenstate?
Yes. And that is not entirely beyond group theory, and it's what I wanted to answer, but our time is running out fast. So I think this is not in Daniel's notes, but what you need are projection operators. So, I mean, I could say at the point where you ask your question, you have to actually solve a Hamiltonian. So if you want to calculate the frequencies, you do have to solve a Hamiltonian or a Schrödinger equation. So you have to go away and do the calculations, but you can know what the displacements look like without that. And
Yeah, that is exactly my question.
yes, yeah, there is a tool to do that. And so I'm going to have to translate this from some other notes. And they're in the wrong notation, but we can construct, and I have to say this without proof at this stage, but this would be a great thing for you to look up if you want. I'm going to put a kind of operator hat on this thing P. For the ith irrep, I can write as Li, the dimension of the irrep, divided by the group order, followed by sum over all group elements of the character in the ith irrep of that group element, multiplying the actual operator of that group element. So that if you act on your basis with this projection operator for irrep I, so this is an operator, so all of this has to act on something. So this operates on your basis vectors. This will give you a new basis vector corresponding to the ith irrep. And it is very hard to justify that in the remaining tiny amount of time, but let me give you a kind of example. So if we take the triangle group, and let's get away from geometrical interpretations for a bit. Let's say that you have a wave function that you want to express as linear combinations of x squared, y squared, xy. So that's a 3D basis. Then our projection operator for A1 would be 1/6 sum of, and then we have to work out the effect of our geometric transforms on x squared and y squared and xy. And let's say we act on x squared first. So we've got our E matrix plus our C3 matrix plus our 2C3 matrix, blah, 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 acting on x squared. And you should find that, well, E acting on x squared is just x squared. The rotation matrix acting on x squared is half x squared plus 3/2 y squared plus an x squared plus a half x squared plus 3/2 y squared. I'm not obviously justifying how I got from here to here, but at least you can see how it would work for the identity. And then if you imagine rotating, x rotates to a proportion of x and a proportion of y according to our matrix cos theta sine theta minus sine theta cos theta. So you apply that, and that's where these numbers are coming from. And the same for the mirror operations. And if we simplify all of that, that's a 6th 3x squared, when you add them up, and 3y squared equals a half x squared plus y squared. Okay, so that linear combination of your original basis states is a state which transforms as A1.
Mm.
And if this guy had been my 9-dimensional vector of atomic coordinates, then what would pop out here would be a 9-dimensional vector corresponding to the A1 mode, expressed in my original basis, but it would now be some weird looking linear combination of my original basis vectors. So my original basis vectors would be 1 followed by 8 noughts, 0, 1 followed by 7 noughts, etc. And this output of this operator would be some linear combination. If I apply projection operator for A2, in this particular example, this acting on x squared equals 0, for example. So it's possible to say that some components of this basis don't contribute to an eigenstate with a certain symmetry. And projection operator for E acting on x squared equals a half x squared minus y squared. And by the way, this demonstrates what I've been saying all along. This is a totally symmetric representation in which this appears added. So this is preserving the symmetries we might originally have had, but here we have a minus sign. So there's clearly a difference. There's more structure here, and this is going to be a 2-dimensional representation. By applying the projection operator to x squared, I've found one of the E states, but I need to apply this projection operator again to somebody else, probably y squared or xy, and I'll get the second of this degenerate pair. So there's one more to be found here still. So if you're going to apply this, I've shown an example of analysis of vibrational modes because I'm guessing that will matter to some people. This would be how to construct the atomic displacements. Won't tell you magnitudes, won't tell you frequencies. That requires a Hamiltonian, but you can know what an A2 mode looks like just by plugging your 9 vector that we started off with into this projection operator. So I'm a little bit over time. Apologies for that. Are there any more questions?
Mainly, I just wanted to ask if you'd be able to share something. I think you alluded to last time that you had some suggestions of your own of possibly suitable level textbooks or sources.
Okay, stay right there. I have to pop downstairs.
Okay.
So everybody has their own personal favourite, and there are textbooks on symmetry and physics written by some very famous guys. So you can pick your generation. So the one that I'm extremely fond of is this one. This is volume 1. With volume 2, you're sort of equipped to tackle more or less all applications of group theory in physics. So that includes continuous groups, Lie algebras, and standard model, particle physics, and so on. We're not going to attempt to go there, but that's my favourite book.
Okay.
But not everybody's. You probably find as many recommendations as there are people attempting to teach this kind of course.
Yeah, that's been one of the problems when I've looked previously to sort of you starting the course. Found so many books, and they, so like you mentioned, some of them just seem so advanced, probably because they're written for mathematicians or hardcore theorists or something.
Yeah,
so it's kind of hard to see which is the right sort of one to pick up, because there's just so many.
Yeah. So what I like about these guys is that they do give most of the proofs. so there are a lot of proofs of things that I haven't shown. This is slightly more formal and rigorous than Daniel's notes, but it covers everything. It's not only about vibrational applications, because that is the easiest application to visualize. And so the chemistry textbooks tend to kind of focus on that, and maybe a little bit on linear combinations of atomic orbitals, which is the kind of thing that I was hinting at with this. You know, you could imagine putting a 1s orbital, a 2s orbital, a 2p orbital, and seeing how they combine and how they're mixed to get symmetry adapted eigenfunctions for a molecule. But the Elliott and Dauber textbook I was talking about goes a little bit beyond that.
Okay, great, thanks.
Yeah, that's a pleasure. I would encourage everyone who's made it through to the end, congratulations, to send any feedback you like to Joanna or to Tom. I'm very happy to have feedback, negative or positive. We're all putting a lot of time and work into this kind of thing, so I would hate it not to be useful for you. And so if we run a course like this again, any comments for improving it are very welcome. So don't be embarrassed to tell people what you think. That'd be very helpful. And I hope it's useful, and I'm happy to try and advise on any applications that you've got in mind, although I may not be an expert in every application of group theory that you're interested in. And in the end, I think this is one of these things that you end up teaching yourself, but you have to have that kind of push to get you started. I had an excellent group theory course when I was an undergraduate, and it's almost one of the reasons why I ended up studying condensed matter physics. So there you go.
Yeah, thanks again for that. It was great.
Pleasure.
Yeah, thank you very much.
Yeah, thanks all for coming along.
It's really, yeah, it's hard from a distance to feel the appreciation maybe, but yeah, thank you, and also for all the examples and yeah, hands-on stuff.
Oh, I'm very happy to do it, and I hope it is useful or becomes useful for you when you've got to grips with it a bit more. There's no assessment, so there are no problem sheets. But if anybody wants some questions to test themselves on, Daniel did construct some, so email me and I can send you them. Okay, so bye everyone, and good luck with your group theory in the future.
Bye.
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 Thank you.
Okay.